Good morning, everybody. I'm going to talk to you today about using scripting in Ansys Mechanical and show how relatively straightforward it can be. And I'm going to do some live demos, really. I'm going to focus on that. And ideally, I'm going to show you some of the power of the scripting interface and what it can be used to enhance your efficiency, make your lives easier as engineers, but also just to give you a sort of fundamental understanding of the processes involved. So I'm very briefly going to introduce the scripting framework and what it represents. The fundamental thing I'd say here is that every part of the model can be accessed with Python. So we're going to look at the Python scripting capability here, and this enables us to programmatically interrogate the models. So all of a sudden we can use programming, we can use Python language to interrogate every feature of our Ansys Mechanical model. This enables us to automate a lot of the things like load generation or meshing. We can do custom results types. We can even do automated pre-solve checking. And so these are some of the features that we're going to cover today. But it's just that fundamental point is that every part of our model can be accessed with Python. So what we're going to do now, we're going to dive straight into mechanical. And what I've got here is it's a fairly simple model. This is just a simple composite model, but we're going to look at some of the aspects of the scripting interface and some of the scripting behind using Python. And so what I'm going to do, I'm going to actually open up, if you've used Ansys Mechanical in the past, so the scripting interface, one of the means of accessing this is through the automation tab. So we go into our automation tab, and then if we enable the scripting interface here, so if we use that toggle button there, you'll see I now get what looks like a very simple IDE or integrated development environment on the right hand side. And this enables me to both generate Python code, but also to use Python commands here to interact with the model. And this is one of the fundamental routes that we would use to get into our scripting. And this then enables me to put in Python commands to generate scripts and to automate features of the design. And this also then enables me to talk to the model that we've got here, so to investigate all different aspects of this model tree and programmatically interrogate that model tree. And so we'll go through some examples of what I exactly mean on that. Now, I'm going to make the presumption or the assumption that most of the audience at least have heard of Python, or if not, have got some level of experience of it. But what we need to do, we need to use Python within Mechanical to start talking to this model. Now, until recently, this had to be done using what's called IronPython. IronPython is a sort of .NET implementation of Python, so it's not the full-featured C Python that you might be used to. It's got pretty much all of the basic commands in there, but we haven't necessarily got access to some of the external libraries. Now, more recently, in recent versions of Ansys, say, I think it's 2022 R2 on, we now also have access to CPython. Now, CPython is probably the Python that you may be familiar with, sort of downloading from python.org. And using that capability, and we'll see that later on, gives us the ability to call in external functionality to use some of the advanced data processing libraries or numerical libraries like NumPy or SciPy. And having that capability really does enhance some of the offerings that we can then customize our mechanical with. For example, I'll show you an example later on of a composite fatigue that I've encoded using an external Python library. So we're going to look at two approaches today. We're going to start off just using fundamentally IronPython. So this is the native Python within the mechanical framework. And then we'll touch on the CPython as well. But really, how do we access that data model? Everything within Python is an object. It's an object-oriented language in many respects. And so what we need to do, we need to generate a Python object, or we need to use Python objects to talk to the model within our Ansys Mechanical. And we can do that quite simply. We can start off, so we can say down in the console, it's called. So any commands that we put in here, we can interact in real time with Ansys Mechanical. So you can see I've used this ext API. This is just effectively an external API command, but really useful. If I then use the sort of Python object notation, so we use the dot notation to get to the object, you can then see I get an autocomplete or a sort of code suggestion of all the functions underneath that object. So if I want to talk to the data model, the data model is pretty much one of the fundamental ways of interrogating this model. So if I do data model and then I do project, you can see the project up here in the tree is pretty much the same here as the name there, isn't it? So if I do project, that's going to give me access to that Python object, which I can then interrogate the model tree with. So if I do name, for example, and let me just do one of the drawbacks with scripting occasionally is that you sometimes have to toggle this twice to enable us to do interactive. So there we go, there's my command. So you can see that when I return on that, it tells me project. So I get the name of this project, which corresponds to this object here. So this root of the model tree. And this is what fundamentally allows me to then navigate around the model tree and use Python to interrogate the model. So for example, and if I use the control key and the up arrow, I can go back to my previous command. So within that project, clearly I've got a model, haven't I? So now I can assume that model, and again, if I just check that by looking at the name, you can see very quickly I can interact with this model. So I've got the name. I'm going to navigate down, just to give you an example, into the geometry branch. So let's have a look at geometry. And if I want to see how many bodies we've got within that geometry, or you can see in here, we can call various commands. So for example, we can get all of the active bodies, and that will then return the Python object that gives us access to all the active bodies. And I can do pretty much everything you would do within the GUI. I can do it programmatically. So I can add in figures, I can add in images, I can add in things like a layered section. So you see I've already got a layered section in here, but if I actually wanted to use Python to generate that layered section, I can then call in add layered section. And you can see very quickly I can then start programmatically using Python to generate features within this model. So this becomes a very, very powerful way of, say for example, you have a consistent model setup that you use on a day-to-day basis. We can actually start generating a script that will automate a lot of that model generation. And because we're using scripts, obviously we can then define variables within that script that can then enable us to flexibly change parameters within that model. So I can change the number of layers within my composite. I can change material assignation, or assignments. So I can change features of the model as it's being generated. And it becomes a really, really powerful way of model generation. Similarly, we can do things like we can solve the models. So we can submit models and get them solved, either locally or on RSMQs or externally. And then we can drag the models back in and we can start doing some automated post-processing. And it all uses this common approach. So you can see within this model, I've got two LS-DYNA analysis blocks. So how might I work out, well, how many analysis blocks have I got in there? Well, then I go to my model, and then I would go to solution. I go to analyses. And if I just do count, see, this is now telling me I've got two analysis systems in there. So what I'm going to do, I'm going to control and up arrow, and I'm just going to focus on, so that returns a list. If I just present it, if I just do that, that gives me a list, a Python list of the two analysis blocks. So if I want to refer to the first analysis block, I would do this. I would index that zero. Python is a zero indexing language. And so you can see now I've got reference there to my first analysis block. So we'll just do a check on that. I quite like to do this really. Let's say name. So you can see, yes, this has picked up LS-DYNA. It doesn't pick up necessarily the cell from Workbench. We can access that cell address from elsewhere, but this is telling me I'm in my LS-DYNA block. And as you can imagine then, I can then start adding different features. So I could add in boundary conditions. I can add in displacements. So I can control what's in my LS-DYNA analysis in this instance. Exactly the same for APDL models, the same approach here. So I can control what's in that model and what loads are applied, what features of the model need to be represented. So again, I can do that programmatically. I can then solve that, and then for the purposes of today, what we can then start doing is actually start looking at some results. So if I do my analyses, you can see this is now the address to that top analysis block. I can then do solution, and then I can say children. So this is going to tell me, and if I do count, this is going to tell me that I've got 26 different children underneath that solution block. So you can see all of these branches of the model tree underneath that solution block are the 26 branches, and this means that I can then start going in and I can use Python to then see what those results types actually are. So if I do children, I'm going to do one, I'm going to say name. So you can see this is now a reference to my x-axis normal stress. So there we go, there's my x-axis normal stresses. And there's a really powerful feature now. I can then start programmatically, or using Python, I can say, for example, we can have a look at the maximum. If I just find the right command. Yeah, here we go, maximum. And you can see I'm getting my return value there of 262 megapascal. So my same 262 megapascals here. What this means is that I could do iterative analysis. I could go and automate the whole analysis procedure from beginning to end just using Python. And I can extract pretty much every feature of the results here. Which you may think, oh, well, what's the use in that, Rich? Why is that particularly useful? Well, in this instance, if you're doing an LS-DYNA, this is a layered shell. So we've got a composite section here on these layered shells. Now, by default, if we're using Ansys Mechanical to post-process this, we can only look at the results at the top, middle, and bottom layers. So there is no native way of post-processing every different layer within this layered shell, just using Ansys Mechanical. Okay, we could do it if we used ACP, so the Ansys Composites pre-post processor, then we could have done some more detailed investigations into the per ply response. But if you haven't got access to ACP, or you need to just use Ansys Mechanical without ACP, or you just need to get access to those individual directional stresses within each of the plies, then I can actually use Python to do that. So I can start adding in functionality to use Python to interrogate the model and to bring in results from an external D3 plot file. And the mechanism by which I do that is to do what's called a Python results type. So you can see if I go to my solution and I can actually insert a Python result type. Now this gives me the capability to then, you can see here I've got my Python result type. And this gives me the capability to interrogate the model in the manner I absolutely need to do it. And you can see there are two tabs now. So here's my geometry tab, which gives me the results in the screen. If I look in this Python result, you can see what I've done in here. I've generated some Python code to then give me the results that I'm really looking for. So what I'm looking for in this instance is stresses at each of the plies within that model. So I use exactly the same Python commands that you've seen me typing into the console down here. In fact, I might get rid of the script now so we can get a better view. So this is my Python result type. So I'm importing various libraries, and you can see in here, this is that ext API command. This now gives me the capability within this Python code here to both talk to the model tree, but also to bring in external results. So I'm then deriving, or I'm generating various variables. So I tell it what the data source is. I give it an ACT units file. This is a sort of a specific thing that you would have to load in to get D3 plot results, for example. And then I'm using what's called the data processing framework. Now, I would refer you back to Thierry's video for a better description of what the data processing framework is. But what it is, it's a very efficient way of using Python to post-process large data sets. And as soon as I set up my Python objects, I can then use what's called DPF operators. So these are really processes that we plug together. So we bring in results, we pass them through operators, they post-process results, and they generate us, say, field output or scalar output or even time history output. So it's a set of Python libraries or Python functionality that does very efficient post-processing results. So for example here I'm saying, yes, I'm going to include some time scoping so I can get the full time history data out. But most importantly, I can also do things like this. So within my Python code, there's another tab here, property provider. And this gives me the capability to actually put on some input parameters or some output parameters in the details panel. So I can now, within the GUI, very quickly generate input and output data that enables the user to interact with my Python script and specify exactly what we want to look at. So you can see in this instance, I've put in a drop-down list for either selecting mesostress or any of the directional stresses. And this can then feed back. You can see in here, I feed back into my Python script. I extract these data from my GUI, and this then means I can prompt the user for input. So I'm going to look at integration point 3 in this instance. Max int value, that's a LS-DYNA specific parameter that tells us how many integration point data are available within the model. And by default, this is functionality that's not present in Mechanical. So now I've got the capability using this really simple Python code to then extract the stress data I want. Now, what I would say is this is a totally neutral model, so I'm more than happy to share this as a worked example on the link that we'll send around. But you can see that it really is straightforward. And what have I got here? I've got 133 lines of Python code. And this is the fundamental one where we're extracting data from our D3 plot file. We're doing a bit of post-processing on it if I want to generate a mesostress. So you can see here we call this function calculate mesostress, which I've defined right at the top. It's just a simple helper function to generate a mesos equivalent stress from the stress components from the stress tensor. And that then enables me to then generate that stress field. And the beauty here is I can then put that back, I can scope that back onto my elements within the GUI or within my model, and I can then display that. So I can then display my stress data at any point in that time history on whichever integration point layer I need to within my LS-DYNA D3 plot file. So what I'm saying here is this is a functionality that's not present within Ansys Mechanical, but it's a really, really easy thing to then set up specific results that I might need. You know, you can see it's almost a trivial amount of code, 133 lines of Python code, all very transparent, easy for the user to then read and check. And this is a very immediate way of starting to customize Ansys Mechanical. Now, what I can also do, when I'm happy with this code, I can come back into my scripting environment, for example. I can recycle that code from here. I can generate, say, a new script. I could do some work in this new script. And if I then want to reuse this a lot of times, I can then add this as a button within the ribbon at the top. So if I want to do this on a sort of almost daily basis, I probably wouldn't go into here and I would say insert Python result. I might not want to do that day to day. So instead, what I might do, I might actually generate a standalone script and then migrate that up and put that as a button in the user interface. The next approach might be, you can see, for example, here we've got ribbons in the top, so we can then take that button code that we might put in the scripting interface, we can migrate that up again to an ACT, so a full developed deployable tool set that we can then include in the GUI in a separate manner. So once you're content with your Python results, then you can actually start migrating this, so we can then deploy that within enterprises. But I think really the power of what I wanted to show today is just the power of this very simple means of interacting with the model using Python, so using our console to get some familiarity and some understanding of the model tree and the structure here. And then using that functionality within things like custom results, for example. Now what we can also do, you'll see the record button, so we can actually generate models and we can record the model generation as we go along. And that will again give me an indication of what's been done here. So that will record all of the Python. And we can then use that Python to then edit it and further enhance and further automate the approaches that we do for model generation, post-processing, solving. But what you might also notice that when I do my insert here, there's a Python result. There's also the capability to do what's called Python code. And this is yet another fundamental way of interacting with the model tree. So then what we can do, we can actually generate Python code that will execute either immediately after the solve was completed, or after anything in the model tree is changed, or after a post-processing operation is completed. I can put in Python code in pretty much every different branch of the model tree, so I can do it here. I can say ls-dynet, insert, Python code, and I always struggle to see this when I'm doing live demos. Here we are. And you can see in this instance, I can actually say, I can run some Python code before solving. Now the reason I show you this is because I have written just some really simple helper script that will do some pre-checks of my model to make sure that all my unit system is consistent, for example, and I've got the right level of mass. So I can even prompt the user here, before this is submitted as an expensive analysis, I can say, look, are you sure that Young's modulus is correct, or that density is correct for this scale of model? And it becomes quite a neat way of doing some pre-checks, or making sure that certain features of the model are actually represented. This is a piece of software or a piece of code that I don't see used on a day-to-day basis by many people, but I do think it's worth knowing that it's there. It can be very, very powerful. And again, we can interact with every feature of the model tree. So we can have Python code in here that would automate a series of loads, for example, or a series of consistent model features that you might do day to day. So these are some of the fundamental ways of using Python to interact with the model. Now I did say that we also have the capability to use CPython. So we've just looked at IronPython. We can also use CPython. Now the commands that you'll have seen are exactly the same with IronPython and CPython. But what I will show you is we can actually then use CPython. And if I bring up this model here, this is just another composite model. But in this instance, I've used a bit of Python code down here. So you can see I've got a couple of things in here. I've got a composite fatigue Python result type. And the reason I'm showing you this is because, again, composite fatigue is not necessarily supported natively in Mechanical. There are encoded ways of doing this, but we can actually use CPython. So you can see in this instance, I've got another piece of Python code. But what you'll see there is I'm actually importing some external libraries. So I'm importing NumPy. This is a numerical processing library within Python. It's very well known. I'm importing the math library, but I'm also importing this FatPack library. And this is an interesting thing. So what this is, Fatpack is actually an external Python functionality. So it's written by Mr. Gunstein here. And this is a library that you can install, openly accessible library that you can install that does external Python fatigue calculations. So we can then use that fatigue capability, that external fatigue capability, as a post-processing operation within Python. So I've imported that Fatpack. You can see here I've dragged in some of the composites data processing framework capabilities. I generate my stress operators, so I extract the stresses. I'm then extracting things like the tensor data. But what I can then do down here, I can then interact with the user. So you can see I've got a number of steps, I've got various different parameters, I've got some Fatpack specific SN curve parameters. So this enables me to generate SN data for these materials. I then take those data, I interact, or I take those data from the GUI, and this then enables me to then call functionality within Fatpack to generate damage or to generate fatigue life data. I can then have them as a field. So you can see here I then put my fatigue damage into a field, and I can then do contour plots of that fatigue damage, which is really, really powerful, because I can now, within a very standard Ansys Mechanical, with a fairly limited, again, only 145 lines of code, so not significant code development, I can now have things like fatigue damage on composites. And I can customize that. You know, there's a huge amount of documentation on that Fatpack library, so I can customize this to exactly the sort of results I need to show. Now, there's a second interesting thing to consider here. I can also do, if I'm doing code compliant work, so for example, if I'm looking at the DNV composites responses, there's some factors within, this is a DNV, it's an offshore standard. So if you're ever doing code compliant and you need to generate code compliant results, in this instance, for example, it's a modification of the basic Tsai-Wu criterion, which uses some other interaction parameters. Well, same applies. I can have my user interface down here, so I can get those HXX coefficients or my gamma coefficients, and I can encode the calculations from within that DNV code compliance, or whatever code you need to write to provide results for. I can write Python functionality that will then take my gamma and my H12 and H13 star parameters. It will follow the calculation methods, or I've encoded here the calculation methods presented in that DNV code. So you can see down here I'm then using that to generate my strength index, for example, my strength ratios, and ultimately enabling me to do plots that would be consistent with that code that code requirement, but gives me an overall contour plot. You know, conventionally I may have had to extract these data and put them into Excel and then just generate Excel plots or Excel data. I can now have this as a self-contained workbench archive that gives me my code compliant results. So you can see again, really, really powerful way of using Python results or Python functionality to generate custom results types that enable me to then have nice, and you can see that we can then utilize the graphical capabilities in Mechanical to give nice interaction, good plots, good quality plots for reports, but with a consistent approach. It also means I reduce the likelihood of any human error with cutting and pasting data into or from Excel. So it can be a phenomenally powerful way of interacting with Mechanical. It's a really, really difficult subject to summarize and to say, but what I'd like to think is I've given a sort of brief introduction into some of the capabilities here of using Python within Ansys. And not just the Iron Python, not just the native Python, but we've now got this capability to access external libraries. So we can do some fairly advanced data processing and process huge amounts of data really efficiently in small amounts of code. And you can see it then gives me the capability to then give things like code compliant results. So I have a summary file here. So yeah, these are the two demonstrations we've done. We've had a quick look at the basic interface, and we've then gone and looked at some fat packs, so the composite fatigue, and we've talked about even further customizing and doing code compliant results. But thank you very much for your time. I'm very grateful for you watching this.